du département des sciences mathématiques et naturelles de l'Académie tunisienne des sciences, des lettres et des arts, nous avons l'immense plaisir d'assister à la conférence du professeur Baklouti sur la théorie de Lie, les déformations et sciences de la nature, à l'occasion de la remise du prix Pfizer 2024, décerné par la Royal Society de Londres. Et c'est à 18h30, heure tunisienne, et 18h30, heure de Londres. Donc, le prix Pfizer 2024 de la Royal Society est décerné au professeur Ali Baklouti pour ses travaux sur l'analyse harmonique non commutative et la géométrie sur les espaces homogènes. Cette conférence explore le rôle fondamental de la théorie de Lie dans l'avancement de divers domaines scientifiques, en particulier ceux liés au système vivant. Un aspect clé de cette contribution réside dans la théorie de la déformation qui améliore notre compréhension des systèmes et de leur transformation dans diverses disciplines, essentiellement la biologie et la médecine. Donc, nous allons nous connecter directement au Royal Society de Londres pour assister à cette cérémonie exceptionnelle qui honore tous les mathématiciens tunisiens, les enseignants-chercheurs tunisiens et la Tunisie, et plus particulièrement l'Académie. On va être directement maintenant en connexion avec la Royal Society de Londres. Merci.
Okay, welcome everybody. Thank you for joining us today. I'm Sofiane Kamoun. I'm a Tunisian based in UK. I work at the Sainsbury Lab in Norwich. I'm not a mathematician, I'm a biologist, and I'm here as a fellow of the Royal Society and also to chair this session today, which is for the African Prize Lecture. Huge honor for me to be here. Before we move on, I want to welcome His Excellency, Yassine El-Oued, who is joining us here as the ambassador of Tunisia to the United Kingdom, and also, of course, many other guests here and honored guests and fellows. So a huge pleasure really to be here. But before I get with the details of the lecture, there's some housekeeping items I have to do. And I want to first invite you to switch off your mobile phones. I just realized I didn't switch off mine, so I'll make sure I'll do that. So let's switch off our mobile phones here. And this, keep in mind that this is recorded, so please do make sure your phones are off. And also, there is no planned fire evacuation or fire alarm. So if there is an event of an alarm, please do move out of the building. There is no specific assembly point except to go, when you walk out of the building, go to the right and then up the stairs, Duke of York stairs, facing the park. Then we should assemble there in an eventful and likely case of a fire alarm. And then keep in mind that there will be a Q&A session at the end after the lecture. And for that, we'll invite you to ask questions. There will be microphone runners. And so please use the microphones. Make sure to use the microphones to ask your questions because, again, it's recorded. So we need everyone online to hear that. And also, those of you online, please use the Slido to ask questions, and the code is hashtag AP2005. So hashtag AP2005. Okay, with all that, it's an incredible pleasure today to welcome Professor Ali Baklouti, who joined us from Tunisia. And today, I think the Royal Society is in the colors of Tunisia. You know, the red color of Tunisia is present at the Royal Society. So Professor Baklouti, as you all know, is a mathematician. And today he's here to present the Royal Society Africa Prize Lecture. And I want to say a few things about the prize itself. This is a relatively new initiative by the Royal Society. It's really wonderful that the Royal Society does this. It started in 2019 and it's been given annually. And this Royal Society Africa Prize recognizes research scientists that are based in Africa and who made innovative contribution to science. And the prize is intended for scientists at the senior stage of their research career with the potential to build research projects to follow on from the prize itself. And this year, we're really proud to award the prize to Professor Baklouti. Tonight's lecture, as you can see there, will be on Lie theory, deformation, and also applications to the life sciences. And this will be the Africa Prize for 2025. A few things about Professor Baklouti before we invite him to the podium. So he's a full professor of mathematics at the University of Sfax, Tunisia. I should mention that Sfax is my father's hometown, so I originate from Sfax, so it's a double pleasure here to welcome Professor Baklouti. And Sfax has a reputation in Tunisia of having being very serious work ethic, and also usually the highest, most educated people tend to come from Sfax, but it's not a surprise, anyways, that Professor Baklouti is from Sfax. Since 2012, Professor Baklouti has been become 2022 award and medal. Category A in mathematics, recently appointed as holder of the chair. This will actually kick in. And also he was recognized by Tunisia as Order of Merit for Education and Teaching by the President of the Republic of Tunisia. So with all that, an incredible honor. I'm going to say a few words in Tunisian because this is being recorded. I want this to be for posterity. So, Sali, مرحبا بيك في لندن، مرحبا بيك في Royal Society. شرفتنا، شرفت تونس، شرفت صفاقس، شرفت الأمة الإفريقية والعربية. مبروك، مرحبا بيك. Welcome, Sali Baklouti.
Okay, thank you very much, Sofiane, for this nice introduction. I'm very pleased to welcome all of you coming for this lecture today. So, first of all, this is a great honor that I have been awarded by the Royal Society. And deep thanks to all the staffs here for organizing this prestigious ceremony. And I would like to thank especially His Excellency, our Ambassador of Tunisia in London, Mr. Yassine El-Oued, and all the staffs of the embassy. So it is a big honor that they are here to help. So they represent our country, they represent Tunisia, and this is big moments actually to share together. I would like also to thank many people here coming from far away. Professor Kamel Barkawi from Paris, great honor also. Thank you very much. So he's a member of Tunisian Academy of Science, Letters and Others. This is a pleasure. Dr. Mohsen Ben Shibani from Brussels. Thank you very much for coming. So he's also the president of the Association of Sustainable Development, for which I am a member right now. And Professor Dominique Manchon from Clermont-Ferrand. And also great thanks to Professor Sadaq Khalal, first of all, for constant help and for steady endeavors for mathematics in Tunisia. And thank you very much, Sadaq, for your nomination. I would like also to thank all people attending online. My friends, my colleagues, so especially our colleague from the Academy of the Tunisian Academy of Science, Letters and Arts. So they are watching online this ceremony. I thank them very much. And also I would like to extend some moments first to the memory of my parents. I think they would have been very happy to see this moment. And to my family, starting with my wife, Professor Aqila Baklouti Salami, who is a professor in linguistics, present here in the room. And also my daughter, Zainab Baklouti, Dr. Zainab Baklouti. And my sons, Marwan Baklouti from Lyon, France. And also my sons, Farouk Baklouti from Poland. So I thank them very much. I dedicate this award to my family, to my country, to the African community, and also to the mathematical community. So this is, I would say, for the Royal Society, this is the first time that the mathematician get this prize. So it is very honorable for mathematics and for the developing of knowledge around the globe. Now let me start a little bit this lecture. So as you see, this is about Lie theory and some developments and some impact about what can be done with Lie theory about some life sciences and some natural sciences. So I would like to say some word about the research profile of Ali Baklouti. So Ali Baklouti is a professor of mathematics. So my primary research interest lies in the intersection of algebra and analysis. I'm working on representation theory of solvable Lie groups and non-commutative harmonic analysis. So actually, the Herbert's method introduced by Kirillov in 1962 was a very powerful tool to, first of all, consider this harmonic analysis around the nilpotent Lie groups and exponential solvable group, and also for solvable Lie groups. My second area of research is geometry, with emphasis on deformation theory of discontinuous groups, with focus on some pioneering contributions by Professor Toshiyuki Kobayashi from Tokyo University, and with deep connections with topology, rich framework, rigidity, and stability of geometric structure. Of course, for a lot of you, this is a little bit strange, something which is not understandable, but don't worry, I will go through some applications, and fundamentally, this is the main question. So how to make this mathematical accessible to a lot of people here, because it's quite a bit complicated to explain mathematics to general audience. So the challenge lies in the intersection of analysis, geometry and algebra, and they continue to inspire a wide array of mathematical investigations. And for nearly 3 decades, my research has been devoted to exploring and resolving a number of long-standing and fundamental problems within this context. So first of all, this question of closed and of Pukansky polarization is a big and long-standing problems. So during my thesis, I constructed some intertwining operators between 2 unit representations reducible in the setting of nilpotent Lie group. But when you go up to more complicated context, this is the problem becomes very, very complicated. And also, Duflo polynomial conjecture. So Michel Duflo is a French mathematician. I'm very happy that he's watching us online now. And by the end of this talk, I'm very happy to say that we are capable to solve this conjecture called the Duflo polynomial conjecture. And also the Benson-Radcliffe conjecture. This concerns actually some dequantizations problems. The Corwin-Griliff conjecture, I will explain a little bit later. And the 2 polynomial conjecture for restrictions, so followed some work I did during my thesis. And finally, the Zariski closure conjecture. I'm working with Professor Dominique Monchon here. So all these problems actually are based on a theory which is called Lie theory. I think very much my advisor and my first collaborator, Professor John Ledwig from Metz University. So up to now, he's an emeritus professor. And he's actually my first co-author till 2025. But by the end of this year, Professor Idinuri Fujiwara is my first collaborator. So he's the referee of my PhD thesis. And in majority, all these problems and conjectures, we pursued long collaboration to try to have these solutions to these difficult problems and so on. So I thank them very much because they are watching us online. For the problem about geometry and the discontinuous problems around these actions on discontinuous space, etc., I would like to thank all my students in Sfax University and collaborators because they did a very, very nice job about this difficult problem. Also, I will explain a little bit what is the originality of this problem and what are the outcomes and what are the impacts of these problems on life sciences and so on. So the plan of the talk today is something like that. What is the Lie theory? I explain in, let's say, clear way for people who are not originated, who are not based in mathematics. So this is very important. And then I explain what is the impact of Lie theory in life science or life sciences. And there is a big necessity how to go from groups through homogeneous spaces. And this is also very important. And I will explain our contributions about the deformation theory and some outcomes. And finally, I will cite these solutions to this long-standing problem in the last slides. So what is Lie theory? So first, a Norwegian mathematician named Lie was looking at differential equations, something like that. And he wanted to solve them in a single unified way using continuous symmetries. Of course, I think almost everybody in this room knows about what is the differential equation. So just equation when you have something which moves, so behind you have some equation which is called differential equation. So Lie wanted to solve all this equation using a uniform theory called continuous symmetries. But why continuous symmetries? So he was inspired by an earlier mathematician, Galois, French mathematician, who was studying polynomial equations of this type. And he used discrete symmetries. Why discrete? Because in the setting of polynomial equations, you have only finite number of roots of these polynomials. And for instance, if you look at the setting when n equal 2, you have only two roots, and it is very easy to have some groups which acts on these roots. So Sophus Lie wanted to replicate the success of Galois theory and made the analogy between differential and polynomial equations. And why this? Because when it concerns this differential equation, there is in general a continuous family of solutions. And it is only when you specify the initial conditions that you have a single one. You look at here. Yeah, maybe. So you look at here, you have some x's as a continuous symmetry. So the idea comes how to build some group of symmetries around in order to have some solution to these general differential equations. So the idea is to construct or to go through a very easy concept, which is called the group. What is a group? So a group is a set where we can multiply. So just to take two elements of the group and the multiplication of these two elements has a meaning. And the product is still another element of G. For instance, the product is associative like the real numbers. And you have a unity element, which is actually inactive element, just the element 1 in the case of the real line. When you multiply 1 by any element y, point x equal x. So this is very easy to understand. And in this group, we can invert. So if you have any x, so 1 over x exists. For instance, the easiest example is you take the circle, just to take the complex number on the circle, and this satisfies all these axioms. But groups actually manifest themselves through symmetries. I will explain in a moment what does it mean. So they must often appear as symmetry of object, and multiplication is the composition of symmetries. So let me give an example. So if you look at, for instance, the rotation of the sphere around an axis with a determined angle, for instance, you have this x of symmetries. So you have this rotation around this axis, and you can have another rotation. So the multiplication, the composition in this setting has a meaning. So this is our multiplications. You get another rotation around the globe. So the identity element, this is the inactive rotation. So you take any rotation around G equal R theta, and you take the rotation which does not do anything. So it is inactive. And then the result that the product, which is the composition, gives you the first rotation. What is the inverse element? So if you take any rotation, L theta, and you look at this inverse, R minus theta. So the composition, the multiplication, gives you the inactive element, the identity element. So this is an example of a group. And the set of all rotations of this sphere is this group, which is noted SO2 of R. This is just a mathematical notation. And if we allow reflections across subspace, we get a bigger group noted O2 of R. I will explain that. What does it mean, reflections? And the Lie group, actually, so it is a beautiful structured puzzle composed of two perfectly interlocked pieces. First of all, it is a group, and then it is a smooth manifold. What does it mean, smooth manifold? It is something like when you can draw some coordinates. So we badly need coordinates on a given group. And the structure of manifold makes the group look like an Euclidean space. And this is used, for instance, when you do integration, differentiation, complex calculus, etc., etc. So this is very useful, but these coordinates would be local, not global, as they say at the setting of R or R2 or etc. But it will be a local coordinates. And these Lie groups are among the most basic and fundamental building blocks at the modern geometry. So you will see that Lie theory is the mathematical study of symmetry groups and their transformation. So it appears whenever such symmetries are found in nature. It provides a powerful framework for analyzing the behavior of these symmetries. So let me explain more the foundational aspect of this theory. For instance, if you look at the Lie group, and you take any point in the Lie group, so the coordinates are drawn on a Cartesian space, said the Lie algebra. So the Lie algebra is just, for instance, if you look at the setting of the circle, so the element, the unity element is E, and the Lie algebra is just the real line. And of course, locally, it is some interval when you can do a lot of things. So the circle is a curved space, and in any point you can trace the tangent space, and you end up with something like a real line. And we can think about higher dimensional examples, and the meaning is similar. It simply means that at the neighborhood of given point does not look a line. So for instance, if you look at these examples, so this is a higher dimensional torus. In any point, you can trace a plane. And in a plane, you can do a lot of things. For instance, for anything of computations or integration and so on. So this is the idea behind a Lie group and Lie algebra. So if I can illustrate this example, if you look at the surface of the Earth, you can imagine that these coordinates can be something like that. So in any point in the Earth, you have something like an Euclidean space, which is the tangent space. And it is equivalent to an illustration of an example of Lie group and Lie algebra. So if you go now for higher dimensional subspaces, so instead of looking at SO2 of R, you can look at S1 of R. And the fact of these groups are manifold means two things, actually. Instead of considering them simply as a set of matrices, we can approach them geometrically. So S1 is a group in itself because it consists as rotation, as I explained before, but we can approach this set of matrices geometrically. And they are among the most fundamental family of Lie groups. For instance, if you complexify, instead of looking at matrices with real entries, you go through complex entries, you can consider, for example, SU of N. This is the Hermitian matrices with some equality of the determinant, something like that. And also a bigger group is SLN. This is of all matrices with the determinant equality. That's very useful, actually, when you look at in terms of applications in many sciences. So, for instance, what is the impact of all this Lie theory in some? For instance, in mathematics, it is almost perfectly well connected. If you look at this kind of domain, algebraic topology, algebraic geometry, combinatorics, differential geometry, number theory, low dimension topology, Riemannian geometry, etc. So these are very related to Lie theory. Also, Lie theory is ubiquitous in physical sciences. So it is associated, for instance, to classical mechanics, electromagnetism, particle physics, quantum theory. And just an application about what I have said about this classical group. For instance, U1 is just the circle. It describes the phase symmetry crucial in electromagnetism. And SU2, it appears in weak interactions and in the theory of angular momentum. And the SU3, it describes the strong force. And the SO3 governs rotational symmetries. SL2C related to the Lorentz group and special relativity. This is just an example how these Lie groups and this theory intervene, for instance, in the physical sciences. In chemistry, same happens, maybe deeply. For instance, if you look at the relationship with the rotational symmetries of molecules and quantum chemistry, SO3, for instance, and SO2, U1, SO2, etc., have a lot of impact about something related to this domain of research. In biology too, if you look at the symmetries of living systems and the molecular biology, the morphogenes, etc., these groups have their impact and their role within this context. But also for medicine, if you look at the problem of disease progression, the drug development, etc. So these Lie groups have a lot of interactions with this kind of research. So the second group had SE3, which I have not defined yet. I will define that in 2 moments. So this is also very important, and this is related to the Euclidean motion groups, positive Euclidean motion group, which has, I will explain that in a moment, how it is important to build the geometrical vision of all this law we are dealing with actually. And also in earth sciences, a lot of domains are related to Lie theory, so it has a deep impact on that. So for instance, seismology, dynamics of geophysical fluids, crystallography and mineralogy, applied tectonics, etc. So now I explain that groups or Lie groups in general are not very sufficient. So we need to move from Lie groups to something which is very complicated, more complicated, let's say, but more efficient, which I call the homogeneous spaces. So in general, a group J acts on its space. It has an action. For instance, in the case of the permutations, polynomial roots, so Galois established the profound notion of Galois groups. So these are permutation groups acting on roots of polynomials in order to have solutions of complicated polynomial equations. And a group can be understood, and it is often best understood through the way it acts on or transforms other mathematical objects. I will explain that by some mathematical animation, let's say. And the most important thing, there is a notion of transitivity of the action of a group on a set, which means physically, simply, that if you take 2 elements of the group, of the space, let's say, you can find a mirror which transforms the first one to the second one. This is the meaning of transitive action of a group in a space. So for the audience, please all the time have in mind that when I speak about group, just a group of symmetry. If you look what happens in this room, there are a lot of group of symmetry which transform a lot of parts to other parts symmetrically. So please have in mind that when I talk about group, this is a group of symmetry. And these transitive equations defines the geometry of this space. So through this space, any transitive equation of a group on X allows us to write down the space X as a homogeneous spaces, G mod H, like that. And H is a closed subgroup of J, which defines the model geometry of X. For instance, Élie Cartan was elected as a foreign member of the Royal Society here in 1947. So he published between the two wars the following very, very nice paragraph. So he said that elementary geometry is essential, the theory of invariance of a certain group, the group of Euclidean motions. So its purpose is indeed to study the properties of figures that are preserved by an arbitrary motions, stating that all motions from a group which expresses in precise language the axiom which, according to which two figures equal to Z are equal to each other's. I will explain that with some mathematical animation. So imagine that you have some geometric forms like that. And I say that two objects are identical in form if we can map each one onto the other by a motion. For instance, these objects are identical in forms. Why indeed? Because if you look at this example, so we have a group action. So this is translation, 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 translation. This is group actions. Translations, 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 translations. Now rotations. So I rotate the object, I rotate it again, I rotate it again, and then I use the reflections I spoke in the very beginning. So with this action of this group, I can identify which objects are identical in form. And if you have many objects like that, by a first group action, you can get this form, but in the second one, you can get this word mathematics. So this group is called the Euclidean motion groups, actually. So the O of 2 are the rotation groups and the reflection groups. And R2 represents the translation. So the semi-direct product consists the Euclidean motion group, which acts transitively on the Euclidean space E2. It is the group of all transformations preserving the geometrical structure of E2, of the Euclidean space. So E2 results in geometry. It is defined by the symmetry determined by the action of E2. And when you have this transitive action, so you have homogeneous spaces I explained before, and these homogeneous spaces lie in the heart of my research. Just as they did nearly 2 centuries ago for Felix Klein, when he formulated his modern and unified definition of geometry. So Felix Klein published this so-called the Erlangen program in 1872, which classified geometry through the lens of transformation groups. So the idea is a homogeneous space for a group is equivalent to the notion of geometry. For instance, what I have explained now about the Euclidean motion group by Élie Cartan, this led to the Euclidean geometry. But of course, you can have another different type of actions. For instance, you can have the affine geometry. So this is the action of the affine group. You can speak about the projective geometry, the action of the projective group, and you can also consider the Riemann geometry. This is the action of local isometries. So the idea is of this Erlangen program is to stimulate the relationship between homogeneous spaces and the geometry. And after that, Albert Stein took the idea of the Erlangen program and interpreted physically. So this is asserted that the laws of nature are invariant under general coordinate transformations. And Einstein modeled the space-time as a pseudo-Riemannian manifold whose curvature reflects the distribution of mass and energy. But the idea comes from this notion or this program elaborated by Felix Klein. And then Élie Cartan adds, saying that this is more philosophical questions. Nature is not absolutely homogeneous. If you think about the natures, the universe, he adds that it is not homogeneous, which means that you cannot find a group acting transitively on this. And then Charles Ersman reflects the realistic complexity of geometric and physical system, and by saying no absolute homogeneity, but rather local homogeneity. So we move from the homogeneity to the local homogeneity. But what is the local? It is something not very complicated. Just you take your space X and you take any point. So this means that around this point you have some neighborhood which is homeomorphic, which is isomorphic to some homogeneous spaces, which is this notion is very important. So we move from the homogeneity to a local homogeneity. In terms, let's formulate it mathematically. So the local geometry of a space is determined by a geometry first. So a Lie group acting locally, continuously, and transitively on some space X. So X is something like Dumodage. And then you have a discrete subgroup acting. So you have a discrete subgroup here acting on this space X to produce another quotient space, which is called a Clifford-Klein forms. And so this continuous means that the action is proper and free. I won't go through details, but just to say that you have smaller group acting transitively with the proper and free actions. So let me give you an example. So, if we generalize the Euclidean motion group by Élie Cartan for n equal 2, so you get the Euclidean group for general n, and this acts transitively on the Euclidean space, and we have the geometry of En produced by the this transitive action, and in this case, so the discrete subgroup would be something like the integers. I think everybody in this room knows about what are integers. So just I think we have to move slowly in order to. Yes, so you have a discrete subgroup of integers acting on the Euclidean space, and the result is a quotient space, which is a torus here, because the action of Zn on this Euclidean space gives you this torus, because the Euclidean space already is homogeneous spaces. And then, so the easiest way to say that is the torus as a set, as a mathematical set, is something which is compact. And locally, so these spaces are locally the same but different globally. This is the idea. So to move from local to global, so you get, so any geometric structure in the space X is inherited by the Clifford claim forms. So for instance, I generated this image with artificial intelligence to show you how complicated and how sophisticated one can get some Clifford claim forms, which are very, very important, first of all, in nature and in mathematics. And now building on the foundational notions of groups, manifold, geometry, and the profound interplay between them, my contributions focus on advancing the deformation theory of Clifford claim forms within the setting of solvable Lie groups and their compact extensions. So this framework offers a concrete approach to tackling the local rigidity conjecture. So for instance, the Erlangen's program states that geometry is if you have a space and you have a transitive action, so group of transformations, so the deformation is something like equivalent to a geometry, which is equivalent to homogeneous space, and then a discontinuous group actions. And my framework is lying with Lie groups, and the classification of Lie groups give this kind, so abelian, nilpointed, exponential, solvable, reductive, semi-sample, and sample. And I'm working in this area of solvable Lie group, but also I consider some compact extension from some reductive Lie group acting on solvable groups. For instance, the setting of the Euclidean motion groups, you have the compact group of the rotation group acting on R2, which is a compact extension in some sense of R2. So the local rigidity conjecture says that whenever you have a simply connected Lie group and you have gamma, which is not revealed, so this discrete subgroup, which is a discontinuous gradient on the homogeneous space, then I believe that in this case, the Clifford claim form deforms continuously. Let me explain a little bit in a, let's say, more explicit way. So imagine that, you have some homogeneous spaces and you have some actions, and this conjecture would say that there is an infinite continuous way to deform the discrete subgroup gamma with the assumption that the geometric structure of the deformed Clifford claim are preserved. So this is, for instance, the first one is the deformation, the first deformation, but you can get a new one. And then you can get another one. And the conjecture says, in some circumstances, there is an infinite way to deform these Clifford claim forms. This is the conjecture. And unfortunately, the proof resists so far. So I will give you some examples, which is very simple. So if you look at the situation of the plane, G equals R2, and you have the x-axis is our H, and the y-axis is G mod H, and you look at this group, gamma is the integers. Then in this case, two orbits, the positive orbit, so the parameter space is formed by two orbits, the positive orbit and the negative orbit. And in this case, there are only two deformations of the torus. So you cannot deform the Clifford claim form in this case with an infinite way. And the reason is that this group is not nilpotent. Nilpotent in some explicit way, it is, let's say, if I illustrate this example, this means that it is characterized by some polynomial coordinates, something like that. And I published in 2022 first book to explain the dynamics of all these deformations in the setting of compact extension of solvable Lie group, how this works, how this conjecture can solve a lot of several problems. And this year, last month, I published the second version of this book, where I explain the geometry of Clifford clay forms and also the local rigidity and the stability concepts. So in this book, you find, for instance, a lot of things about the structure theory of solvable Lie groups, various geometric and topological concepts related to the deformation and moduli spaces of discontinuous group actions, the newest approaches and methods in deformation theory in the setting of compact extension of solvable Lie groups, the locally rigid conjecture in the setting of compact extensions. So I extend a little bit the setting of this conjecture from nilpotent to the extension, compact extension of nilpotent with some other conditions. And also I explain the notion, the geometrical notion of stability, Hausdorff-Neufs, and the Calabi-Marcus phenomena. And just to say that this deformation theory has a lot of application, for instance, in physics for general relativity and liquid crystals, in chemistry for crystallography and molecular reactions, in biology, proteins and biomolecular structures, in medicine, etc. So this is just some examples, but if you go through the literature, so the application of this deformation theory is really has wide spectrum. And I end this presentation to say some words about these problems I have mentioned in the very beginning. And just to say that the representation theory is a way to understand abstract mathematical objects by expressing them as transformations so that we can work with them more easily. And mathematically, this means that a unitary representation of a group is a pair pi h. H is a Hilbert space, and you have a group homomorphisms. And we use, when you move from the classical harmonic analysis, for instance, from the Fourier analysis, when you have this Fourier transform to the infinite dimensional Fourier transform, you need these representations. So the non-commutative analog of the Fourier transform in the setting of non-commutative group is this one. And I would like to thank all my students working on this area. So they did very, very nice job in how to prove some non-commutative versions of insanity principles that govern the trade-off between localization in group and representation space. So they really did very, very nice job. And the group here acts on the dual vector space of the Lie algebra, and they produce some quadrant orbits. So these quadrant orbits are smooth manifolds, and so this image shows you a layer of quadrant orbits which are smooth manifolds, and they have all odd dimension, and they have related symplectic forms. And the question now is about quantization and dequantization. So how? In order to qualify, so in the Kirillov method, I mentioned it in the first slide, characterize unitary representation as corresponding to a unique quadrant orbit. And the problem is there, how to make this problem of quantization and dequantization. And for induced representations and restricted representations, they are the most typically kind of representations. And we published with Professor Jean Ledwix and Iduneri Fujiwara this book in 2022, and we explain all the harmonic analysis around these representations, and all these representations are related to algebra of differential operators, which are quite a bit complicated, but they allow, at least in a physical way, to get some solution to many, many differential equations and so on. And finally, so I am very pleased to announce that, for instance, for the first problem of closedness of the product of Pukansky positions. So in my thesis, I solved the problem of how to find the neutralizing operation with two representations. And now this problem is completed for the exponential setting case this year. The Duflo polynomial conjecture is, I'm very pleased to announce that it is solved, at least for nilpotent situations. And two papers are underway with Professor Fujiwara. to complete the exponential setting. I gave a counterexample to the dense Radcliffe conjecture, saying that the dequantization process using the cohomological invariant are not very efficient in many cases. And also the parallel conjecture for restrictions also. So it is solved. So this is how to go from induced to restricted representations. And also finally, the Zariski closure conjecture for exponential solvable block. I'm very pleased to say that it is completely solved this year. I think Dominique Marchand, so a revised paper already, and a second in progress looking at the sub-general situations. And let me thank you very much for your listening.
So much. Thank you. Congratulations.
Yeah.
Thank you for this wonderful lecture.
Yeah.
Next is the Q&A session. And before we start with your questions, we have a couple of colleagues from Tunisia who have been watching, I think, live the lecture. And the first one is a speech, actually commentary from Professor Hafid Abdelmelek, who is the president of the Department of Mathematical and Natural Sciences in the Tunisian Academy of Sciences, of Letters and Arts. And this is known as Beit al-Hikma, the House of Wisdom in Tunisia. I don't know if we will have the... we have to do something here? Yeah. There we go. So unfortunately, we don't have the time to go through the full speech, but okay, we have to play. No. Can we move to the next slide? Is that? Here we go. Okay. So this is the speech. So again, not possible to read through all of it given time, but essentially he's recognizing the award and the prize to Professor Baklouti, and also he's highlighting the connections between the different communities and different scientific academies. And hopefully this will also be a stage for further interactions between the Royal Society and the Tunisian Academy, which I think we're all very passionate about, especially here, the Tunisian community in the UK. We've been working really hard to create a stronger link and reinforce the links between the two communities. So thank you so much, Professor Abdelmelek, for these comments. And we have a second guest from Tunisia, and I think, is that on the slide? Are you going to tell the question? So I think, yep.
Questions by Professor Amal Benamar Al-Gaid, who is a permanent member of the Department of Mathematical and Natural Sciences at the Tunisian Academy of Sciences, Letters and Arts. So his first question is, how can deformation theory within Lie groups be used to model adaptive biological systems, such as immune response or neural plasticity, in a mathematically rigorous way?
Yeah, thank you very much. So we have explained, first of all, the impact of Lie theory on a lot of domains in biology, in medicine. And the deformation theory, as explained in this lecture, also can be, so the actions of these discontinuous groups comes basically from symmetry groups, which act around a lot of domains in biology and in medicine. We cannot predict precisely how we can use this theory unless we can modelize correctly the problems. So once we have modelized correctly the problems and we built the necessity framework, the necessity arsenal about all these problems, we can produce a lot of solutions, as they explain in this lecture, to a lot of problems around the questions.
Thank you. And his second question is, how might advances in Lie theory contribute to the development of personalized medicine, particularly in modeling the dynamic transformations of biological systems?
Yeah, same kind of question and same kind of, so we have to actually to modelize. Once we have modelized the problem and look at the circumstances and the difficulties, we can precisely look how to predict these transformation groups and these symmetry groups to solve a lot of problem around these questions. Yeah. Thank you very much.
Thank you. That was one question. Any questions here from the audience? Please raise your hand if you have any questions. Please wait for the microphone.
For this, remember me all this PhD past, I don't know, 20 years ago, no, 30 years ago.
Yeah.
Yeah. I'm working on AI actually, and I can several times I think about all these symmetries that we have in we apply through this Lie theory, and so I'm thinking if you are looking at it, see how you can apply that in modeling, but in data-driven modeling, or interacting with some.
In a precise way, I cannot answer directly this question because this is not my scope for the moment. But what we can say that whenever you look at some local isometries on sharp spaces and sharp problems, you can get a lot of solutions. For instance, the problem of solving these differential operators problems in some complicated space give you some solutions to a lot of differential equations. And I guess, as I answered the first question, we have to modelize the problem. We have to look at the nature of the action. What are the groups which have the capability to act transitively, freely, properly on a lot of components, and then we can predict the nature of answers.
Yeah, exactly. It's like exactly that. We need to get some presentation of all this data in a way we can get this natural presentation of.
Yeah. No problem. Yeah, thank you.
Question here?
Thank you. Thank you, Professor Baklouti, for this interesting presentation and for nicely showing the application of Lie groups to other sciences, physics, chemistry, medicine. And I was just wondering if you are aware of any applications to human sciences of the theory of groups to human sciences, sociology, psychology, if there are any applications and if you are aware of them. Thank you very much.
Yeah, especially for Lie theory, I don't know, but the impact of mathematics is very large on how to develop the human sciences, for instance, because mathematics now is science of logic, and mathematics can modelize a lot of things. And if you think about how to make some statistics or how to make some, so mathematics is everywhere. And I think, so I made the presentation a couple of days ago about the role of mathematics in general on how the human sciences can be touched by this science. So for sure, when you look about how mathematics can affect a lot of sciences, for instance, because it is related directly to, for instance, to cryptography, it is related to data science, probability, statistics. So it has a lot of implication, including the human sciences. Yeah.
Thank you so much for this talk. So you earlier mentioned that SO2 describes the symmetries of an electromagnetic system. I want to know if these nilpotent groups that you mentioned earlier, sort of model symmetries in a certain kind of physical system as well.
Yes. So SO2 is very well known to act about a lot of Euclidean geometry, because SO2, so it is the set of all rotation, positive rotation, let's say, not reflections, acting in the Euclidean spaces, the usual Euclidean spaces, so R2 in our spaces. So it can model a lot of phenomena about physical systems and about something like some local phenomena acting in chemistry, in biology, and so on. So it has a deep impact. That's why Elie Cartan specified his saying about this group, because it has on many things.
Yeah. What about these nilpotent groups that you spoke about?
Yeah, nilpotent group means that the groups is diffeomorphic to something like RD, but with the polynomial coordinates. For instance, the group I mentioned, the group R2. So this it's exponential. It's not nilpotent. So this means that when so I say when I defined a group that there is a multiplication law. When you take two elements, so x point y, this is an element of the group. But if this element depends polynomially on the first one, this is called a nilpotent groups. So the application, so the multiplication is polynomial. So first the group is isomorphic to something like RD or R2 or R, and then the multiplication group is defined by a polynomial.
Thank you.
Yeah.
Hello, I have a high-level question. So, what is the secret to be a great mathematician? And what is your advice for the next generation in Tunisia that want to follow your path, for example?
Thank you very much. So, the advice I can tell to all young researchers is please be prominent, be perseverant. Please pay a long silent moments in research and don't be in a hurry to publish your papers everywhere. So these moments of silence in thinking deeply about the outcomes of your publications, the outcome of your research, the application of this gives you a lot of advantages. And when you publish your papers in very well-known journals, this counts a lot for you. So for young people, especially people who are now taking away for research experience, so be patient, be prominent, and be perseverant. And this is what happened to me when I started my thesis. So the first result I gained took a lot of time. I didn't get some result from the very beginning, but it took a long time. So I thank Professor John Ludwig following us online now. So we took a lot of time to experience a lot of examples and so on. But my first publication, my good publication, took a lot of time to be done.
Okay.
Okay, one last question because I think we're running out of time. Yeah, sorry. I'm not really an expert in this, but protein folding, so predicting protein structure from the amino acid sequence. So AlphaFold made some great progress in there, but they did it in this very messy computational way where it's really try and error, wiggling things around. Do you think with your theory of Lie groups, you could develop more of a theoretical way of predicting protein structures?
Very nice question, yes. So the problem is also when you deal with Lie groups and when you look at first examples, so sometimes it is very complicated to pursue a long computation and so on. And the idea is to have some groups of permutations acting on something facilitates a lot of things. For instance, in the case of Galois, so the solution of all these polynomial equations, so the actions of these groups facilitated a lot the finding of the solutions. But as I said before, for all the questions, you have first to modelize the problem, to look what are the action, necessary action and sufficient action and prominent action, which could give you a lot of solution and a lot of ways to find your solutions and to find the results.
Okay, thank you.
Yeah.
Excellent. Thank you so much.
Thank you.
Let's thank Professor Baklouti again. Now we have a little special moment, and I think I have to read a formal statement here before we move to that. So, the Royal Society Africa Prize is awarded to Professor Ali Baklouti for his work of non-cumulative harmonic analysis and geometry on homogeneous spaces. Again, let's all thank Professor Baklouti and congratulate him again. It's my great honor to offer the medal. So let's maybe move here.
Yeah,
for the photos. So.
Thank you very much. Okay. Well done.
I think this closes the event, isn't it? Yeah, okay. Harry is saying yes. Okay, we'll go. Thank you so much for coming and for joining us today. What a wonderful celebration of science and mathematics and intercontinental collaborations. Thank you.
Thank you very much.
Chers collègues, honorable assistance, j'ai l'immense plaisir, bien sûr, d'assister à cette cérémonie de remise de prix Pfizer 2024 à Monsieur le professeur Ali Baklouti, accompagné par Professeur Amel Ben Ammar Gaïd, membre du département des sciences, et Monsieur le professeur Hassan Al-Amri, membre du même département. On félicite c'est Ali Baklouti pour ce prix, et ce prix, en fin de compte, honore l'école de mathématiques tunisienne et honore la Tunisie. On vous remercie pour votre participation et j'espère bien qu'on aura d'autres prix à l'Académie Beit al-Hikma. Merci.